Venus looks like Earth's twin from space, but that illusion hides one of the most hostile environments in the entire solar system. If you could survive long enough to experience it, you'd find a planet with crushing pressure, corrosive clouds, and surface conditions that would destroy any known spacecraft in hours. Today, we're breaking down what makes Venus a world of extreme heat, toxic atmosphere, and relentless planetary chaos. Earth's evil twin. Venus has been known since ancient times, long before humans understood what planets really were, and it stood out in the sky because it is extremely bright compared to everything except the moon. Early people saw it as a moving light that changed position in the sky but never disappeared for long, and this made it both familiar and confusing at the same time. It appears either shortly before sunrise or shortly after sunset, which is why early observers thought it was two separate objects instead of one planet. Over time, careful tracking showed that these two stars were actually the same object, moving around the Sun in a fixed orbit. This was one of the earliest steps in understanding that Venus is a planet like Earth and not a wandering light or fixed star. Ancient Babylonian astronomers were among the first to record Venus in a systematic way, tracking its movement with surprising accuracy for their time. They noticed its repeating cycle and treated it as an important celestial object tied to their calendar systems. In ancient Greece, this confusion continued for a long time, where Venus was called both the morning and evening star, as if they were two different bodies. Later observations showed that these two identities were the same object, which was a major correction in early astronomy. This helped shape the early idea that celestial objects follow predictable paths rather than random motion. Venus became even more important when early astronomers like Galileo Galilei used telescopes to study it in detail. Galileo observed that Venus shows phases similar to the Moon, meaning it changes shape depending on its position relative to Earth and the Sun. This observation was extremely important because it proved that Venus orbits the Sun and not Earth, supporting the heliocentric model of the solar system. It was one of the strongest early pieces of evidence against the older Earth-centered view of the universe. This single discovery changed how scientists understood not only Venus, but the structure of the entire solar system. As telescope technology improved, Venus remained frustrating because its surface could never be seen directly, no matter how powerful the instruments became. Instead of showing surface details like Mars or the Moon, Venus always appeared as a smooth, bright disk covered in thick clouds. These clouds completely block visible light, making the planet's surface invisible from Earth at all times. This created a long period of mystery where scientists could only guess what lay beneath the atmosphere. Because Venus was similar in size to Earth, many believed it might still be Earth-like under those clouds. By the 1800s and early 1900s, this belief became stronger as scientists tried to model Venus based on limited data. Since Venus reflects a large amount of sunlight, it was assumed to have a thick atmosphere that might support warm, wet conditions. Many theories described Venus as a swamp world or a planet covered in oceans and dense vegetation. Some even imagined it as a younger version of Earth with tropical environments and heavy rainfall. These ideas were not random guesses, but logical conclusions based on the limited tools available at the time. Venus is often called Earth's twin because the two planets are very similar in size, mass, and gravity. Venus is only slightly smaller than Earth, and its gravity is about 90% of Earth's, meaning a person would feel almost the same weight on its surface. It is also a rocky planet with a similar internal structure, including a metal core and silicate mantle. Because of these similarities, early scientists believed Venus might share a similar history with Earth. This made it one of the strongest candidates in the search for extraterrestrial life in the early solar system models. Despite these similarities, Venus behaves very differently when studied in detail, especially its motion and rotation. It rotates extremely slowly, taking about 243 Earth days to complete one spin, which is longer than its year around the Sun. Even more unusual, it rotates in the opposite direction compared to most planets, meaning the Sun would rise in the west if it were visible through the clouds. This backward rotation is called retrograde rotation and remains one of the strange features of Venus. It suggests that the planet experienced major changes or collisions in its distant past. Radar observations later confirmed more details about Venus that could not be seen with normal telescopes. These radar studies showed the shape of the surface beneath the clouds and revealed large plains, highlands, and volcanic structures. Unlike Earth, there are very few impact craters, which suggest the surface may have been reshaped by volcanic activity. Some areas appear extremely smooth, as if lava once flowed across them and covered older terrain. These findings change Venus from a mysterious twin of Earth into a world shaped by extreme geological processes. As radar data improved, scientists also confirmed that Venus has a very thick atmosphere made mostly of carbon dioxide. This atmosphere creates a strong greenhouse effect, trapping heat and preventing it from escaping into space. The result is a surface temperature of around 475 degrees Celsius, hot enough to melt lead and other metals. This extreme heat is present across the entire planet, day and night. Because the thick atmosphere distributes heat evenly, this made Venus the hottest planet in the solar system, even hotter than Mercury, which is much closer to the Sun. The clouds of Venus add another layer of danger because they are not made of water but of sulfuric acid. These acid droplets form in the upper atmosphere and create thick cloud layers that reflect sunlight and hide the surface completely. If a spacecraft passes through these clouds, it must survive corrosive chemical exposure before even reaching the ground. In addition, any acid rain formed in the upper atmosphere usually evaporates before reaching the surface due to extreme heat below. This creates a cycle of destructive chemistry that dominates the entire atmosphere. Wind patterns on Venus also behave in a very unusual way, especially in the upper atmosphere where winds can reach speeds of over 300 kilometers per hour. These winds circle the entire planet in just a few Earth days, much faster than the planet's slow rotation. This phenomenon is known as superrotation, where the atmosphere moves much faster than the planet itself. Scientists still study how this energy transfer works because it does not behave like weather systems on Earth. The result is a constant global storm system high above the surface. On the surface, however, conditions are completely different, with almost no wind compared to the upper atmosphere. The thick air near the ground is so dense that it behaves more like a hot fluid than a gas. This creates an environment where sound would travel differently and movement would feel heavy and slow. Any spacecraft landing there would experience crushing pressure instantly, similar to being deep underwater on Earth. This combination of heat and pressure makes the surface one of the most hostile environments ever studied. Because of these extreme conditions, early space missions struggled to survive long enough to send data back to Earth. Many probes sent to Venus were destroyed within minutes after landing or entering the atmosphere. These failures showed that earlier assumptions about Venus were completely wrong, and the planet was far more extreme than expected. However, each mission still provided valuable information before failing, slowly building a clearer picture of the surface conditions. Over time, engineers learned how to build stronger probes capable of surviving longer. The Soviet Venera program eventually achieved the first successful landings on Venus, marking a major breakthrough in planetary exploration. These spacecraft were specially designed with reinforced structures to handle both heat and pressure for short periods of time. Some of them managed to send back the first images from the surface, showing a rocky, dry landscape under a thick orange sky. These images were low quality, but extremely important because they confirmed that Venus is not Earth-like at all. Instead, it is a dry, lifeless world shaped by volcanic rock and extreme atmospheric pressure. Later missions improved on this success and sent back more detailed data, including color images and environmental readings. These results confirmed that temperatures on the surface remain high enough to destroy most materials used in normal spacecraft design. Even communication systems failed quickly due to heat damage and pressure stress. Despite these limitations, the data collected was enough to fully change scientific understanding of Venus. It showed a world completely unlike the early swamp or ocean theories. As more research continued, scientists began to reconstruct how Venus might have evolved into its current state. One leading explanation is that Venus may once have had liquid water on its surface, possibly even oceans similar to Earth. However, rising temperatures caused by solar heating and atmospheric changes likely led to evaporation of these oceans. Water vapor then increased the greenhouse effect, trapping more heat and accelerating the warming process. Over time, this created a runaway cycle that removed all surface water and transformed the planet's atmosphere. Evidence for this comes from measurements of hydrogen isotopes in the atmosphere, which suggest that large amounts of water were lost over time. The remaining atmosphere is now extremely dry and dense with carbon dioxide, showing no signs of liquid water today. This transformation likely happened billions of years ago, long before Earth developed complex life. Venus therefore represents a long-term example of how planetary climates can shift completely under certain conditions. It serves as a natural comparison for understanding climate systems on Earth. Even today, Venus remains an important target for scientific study because it still holds many unanswered questions. Some observations suggest possible volcanic activity, which means the planet may still be changing internally. Radar data has shown signs that certain surface areas may have been recently reshaped by lava flows. If confirmed, this would mean Venus is not completely dead geologically, but still active in extreme ways. This keeps the planet scientifically important even after decades of exploration. Modern space agencies continue to plan new missions to Venus in order to study its atmosphere and surface in greater detail. Agencies like NASA and the European Space Agency are preparing missions that aim to explore the planet using more advanced technology. These missions hope to map the surface more precisely, study atmospheric chemistry, and understand how Venus evolved differently from Earth. New heat-resistant materials and improved instruments may allow spacecraft to survive longer than before. This next stage of exploration aims to finally close many remaining gaps in knowledge. Venus stands today as one of the clearest examples of how similar planets can evolve in completely different ways. It started with almost the same size and structure as Earth, but ended up as a world of crushing pressure and extreme heat. Every new discovery about Venus replaces old ideas with a more accurate and more extreme reality. It is not just a bright object in the sky, but a planet that reveals how fragile planetary balance can be. And as radar finally broke through its clouds, humanity began to see the full truth hidden beneath. Then radar pierced the clouds. The planet hidden under clouds. For most of human history, Venus looked beautiful from a distance. It was bright, smooth, and calm in the night sky, glowing like a white jewel above Earth while hiding everything beneath its thick atmosphere. Early astronomers could see Mars with its dark markings and polar caps, and they could study the Moon with mountains and craters visible through telescopes, but Venus refused to reveal anything at all. No matter how powerful telescopes became, the planet always appeared covered by an endless layer of pale clouds that blocked every view of the surface. Scientists could measure its motion and brightness, but they could not see what existed underneath. That mystery lasted for centuries, and because nobody could see the surface, people imagined oceans, jungles, swamps, and alien life hidden beneath the clouds. The truth turned out to be far worse than anyone expected, because those clouds were not hiding a paradise, but one of the deadliest environments in the entire solar system. The atmosphere of Venus is the main reason the planet became so terrifying. Unlike Earth, where clouds move across an open sky and allow sunlight to reach the ground clearly, Venus is permanently trapped under a global cloud layer that wraps around the entire planet without breaking apart. These clouds stretch for many kilometers above the surface and are so thick that visible light cannot pass through them properly. If a spacecraft approaches Venus from orbit, it does not see mountains or oceans below. It sees only endless pale yellow clouds covering the entire world like a sealed shell. Human eyes looking down from space would never see the surface directly because the atmosphere blocks normal vision completely. The surface of Venus remained hidden until radar technology and space probes finally forced their way through the clouds during the space age. The deeper scientists studied the atmosphere, the more horrifying it became. Venus is made up of about 96% carbon dioxide, with most of the remaining atmosphere being nitrogen, along with smaller amounts of sulfur dioxide and other gases. On Earth, carbon dioxide exists only in small amounts, but on Venus it dominates almost the entire atmosphere. This single difference completely changed the fate of the planet, because carbon dioxide traps heat extremely well. Sunlight enters the atmosphere and heats the planet, but the thick carbon dioxide layer prevents most of that heat from escaping back into space. Over millions and billions of years, the heat built higher and higher until the entire planet became an enormous pressure cooker. Today, the surface temperature on Venus reaches around 475 degrees Celsius, hot enough to melt lead and destroy most electronics within minutes. What makes Venus even more disturbing is that the atmosphere does not simply sit still around the planet. It moves violently. High above the surface, winds race around the planet at enormous speeds, reaching hundreds of kilometers per hour. These winds move much faster than the actual rotation of Venus itself, creating a strange phenomenon called atmospheric superrotation. The planet rotates so slowly that one day on Venus lasts longer than its year. Yet the upper atmosphere circles the planet in only a few Earth days. Scientists still do not fully understand how this happens because it does not behave like weather systems on Earth. The clouds move like a giant spinning storm system, wrapping around the entire planet, creating constant turbulence high in the atmosphere while the surface below remains trapped under heavy, suffocating air. The cloud layers themselves are among the most dangerous features of Venus because they are not made of water like Earth's clouds. Instead, they contain sulfuric acid aerosols, tiny droplets of concentrated acid suspended throughout the atmosphere. These droplets form when sulfur dioxide mixes with small traces of water vapor under sunlight. The result is an atmosphere filled with corrosive chemical clouds stretching across the entire planet. If a human aircraft somehow entered these clouds without protection, the acid would immediately begin attacking exposed materials. Spacecraft sent to Venus had to be specially designed to survive these conditions because normal materials could not withstand long exposure to the atmosphere. Even before reaching the crushing heat near the ground, probes descending through the clouds faced chemical damage from the acidic environment around them. Scientists divide the atmosphere of Venus into several main layers because conditions change dramatically with altitude. The upper cloud decks are the highest visible cloud layers and are where sunlight first reflects off the planet. These upper layers are relatively cooler compared to the surface below, though still dangerous by Earth standards. Winds here are extremely powerful and move continuously around the planet. Beneath these upper layers lies a middle haze region where visibility becomes even worse and sunlight weakens dramatically. Descending farther down, the atmosphere becomes thicker and darker as pressure rises rapidly. The deeper atmosphere near the surface is so dense that it behaves almost like a fluid rather than a normal gas. Any spacecraft entering these lower layers experiences increasing pressure and heat with every kilometer descended. One of the strangest discoveries about Venus is that acid rain exists there, but it never actually reaches the ground. In the upper atmosphere, sulfuric acid droplets can combine into larger drops that begin falling downward like rain. However, As they descend into the hotter lower atmosphere, the extreme temperatures cause the droplets to evaporate long before touching the surface. This means Venus has a type of rain cycle completely unlike Earth's water cycle. Instead of nourishing the planet, the rain forms briefly in the clouds before vanishing again in the deadly heat below. The idea of acid rain evaporating in mid-air before reaching the ground gives Venus an almost unreal quality, as if the planet itself destroys anything before it can survive. Visibility inside the atmosphere is another terrifying problem. Near the upper clouds, sunlight still exists but appears weak and filtered through thick yellow haze. As a probe descends deeper, the atmosphere becomes darker and more oppressive. By the time a spacecraft approaches the surface, visibility becomes extremely poor because the thick atmosphere scatters and absorbs most light. The sky near the ground would appear dim orange or reddish brown due to the way sunlight passes through the dense atmosphere. The horizon would look blurred and distorted, and distant objects would fade quickly into the haze. A human standing there would feel trapped inside a sealed furnace, where even light struggles to move properly through the air. Scientists also believe lightning storms may exist inside the Venusian atmosphere, although this remains difficult to confirm fully. Several missions detected signals that resemble lightning activity, suggesting electrical storms may occur within the clouds. If true, these storms would happen inside a sky already filled with acid clouds and violent winds. Unlike Earth, where thunderstorms are linked to water clouds and weather systems, lightning on Venus may form through completely different chemical and atmospheric processes. Some observations suggest sudden flashes and radio signals inside the atmosphere, while others remain uncertain due to the difficulty of measuring conditions through the thick clouds. Even today, researchers continue debating exactly how active these electrical storms are. The true horror of Venus comes from the greenhouse effect operating on a scale far beyond Earth's climate systems. On Earth, greenhouse gases trap some heat and help keep the planet warm enough for life. Without this effect, Earth would be frozen. On Venus, however, the greenhouse effect became extreme and uncontrollable. The thick carbon dioxide atmosphere trapped enormous amounts of heat until the entire planet overheated permanently. Scientists believe Venus may once have had liquid water on its surface billions of years ago, but as temperatures increased, oceans began evaporating into the atmosphere. Water vapor itself is a greenhouse gas, so this trapped even more heat, causing even more evaporation. The process fed itself continuously until all surface water disappeared and the atmosphere transformed into a runaway greenhouse system. Once this runaway greenhouse process began, Venus could no longer cool itself effectively. On Earth, oceans help regulate temperature and absorb carbon dioxide through geological cycles. But Venus lost its water entirely. Without liquid water, there was no stable carbon cycle to remove carbon dioxide from the atmosphere. Volcanoes likely released enormous amounts of gas over long periods of time, adding even more carbon dioxide into the atmosphere. The heat continued building until the planet reached temperatures capable of melting certain metals. This transformation turned Venus into the hottest planet in the solar system, despite Mercury being closer to the Sun. The thick atmosphere also creates crushing pressure near the surface. On Earth, humans are protected by one atmosphere of pressure, but Venus has about 92 times more pressure at ground level. This means standing on the surface of Venus would feel similar to being nearly 1 kilometre underwater on Earth. Human lungs could not function there, and ordinary spacecraft structures would collapse quickly under the force. The atmosphere presses down with enormous weight because it is both extremely thick and extremely dense. Every object on the surface exists under pressure strong enough to crush most machines unless specially reinforced. When the first spacecraft attempted to study Venus, scientists did not fully understand how extreme these conditions really were. Early probes were designed using limited information, and many failed before even reaching the surface. Some spacecraft lost communication during descent because heat damaged their systems. Others were crushed by pressure before transmitting useful data. Each failed mission revealed another layer of danger hidden beneath the clouds. Engineers realized that Venus was not simply difficult to explore, but actively hostile to machines entering its atmosphere. The American Mariner missions played an important role in revealing the truth about Venus. Mariner 2 became the first successful spacecraft to fly past Venus in 1962, and it completely changed scientific understanding of the planet. Instruments aboard the spacecraft detected extremely high surface temperatures, confirming that Venus was far hotter than scientists had expected. This mission helped prove that the heat came from a strong greenhouse effect rather than direct sunlight alone. It was one of the earliest signs that Venus had evolved into a planetary disaster unlike anything on Earth. Later missions provided even more disturbing information. The Soviet Union launched the Venera program, which became one of the most important efforts in planetary exploration history. These probes were designed specifically to survive the brutal conditions of Venus for as long as possible. Many early Venera spacecraft failed during descent or stopped transmitting shortly after landing, but engineers kept improving their designs. Over time, the probes became stronger and more resistant to heat and pressure. Some eventually survived long enough to send images and scientific measurements directly from the surface. The descent of a Venera probe through the Venusian atmosphere remains one of the most terrifying sequences in space exploration history. As the spacecraft entered the upper atmosphere, it encountered thick clouds and violent turbulence. The temperature outside the probe began rising rapidly, while pressure increased every second. Instruments struggled against the corrosive acid clouds as the parachute slowed the descent. Sunlight faded into deep orange haze as visibility worsened. Deeper into the atmosphere, the air became so dense that the spacecraft descended through conditions more like a hot ocean than a normal atmosphere. Inside the probe, systems were constantly fighting against the environment. Cooling systems attempted to keep electronics alive, while pressure-resistant shells prevented the structure from collapsing. Despite these protections, instruments slowly began failing as the descent continued. Some sensors stopped working from heat damage. Communication systems weakened under the stress. By the time the probe reached the surface, it had already survived conditions that would instantly kill any human being. Yet even on the ground, the struggle continued because the heat outside remained high enough to destroy electronics rapidly. The first images returned from the surface shocked scientists around the world. Instead of oceans or vegetation, the cameras showed a barren, rocky landscape under dim orange light. Large stones and flat volcanic terrain stretched across the surface beneath a thick atmosphere that distorted visibility. The sky looked unnatural, filled with heavy haze and weak sunlight filtering through kilometers of toxic gas. There was no movement of water, no sign of life, and no relief from the crushing pressure and heat. Venus looked less like a planet humans could explore and more like a sealed furnace world. The Pioneer Venus missions added even more detail to the growing understanding of the atmosphere. Pioneer Venus studied the structure and chemistry of the atmosphere in greater depth, using orbiters and probes to measure temperature, pressure, and cloud composition. These missions confirmed the complexity of the cloud layers and revealed how dynamic the atmosphere really was. They also showed how sunlight interacts with the thick clouds and how heat circulates across the planet. The data helped scientists build more accurate models of the runaway greenhouse effect operating on Venus. One of the most disturbing aspects of Venus is how stable its extreme environment has become. Unlike Earth, where temperatures change between day and night, Venus remains incredibly hot almost everywhere all the time. The thick atmosphere traps heat so efficiently that even the dark side of the planet stays nearly as hot as the side facing the sun. There are no cool nights capable of lowering temperatures. The entire world exists in permanent heat and pressure without relief. This stability makes Venus feel less like a changing planet and more like a machine locked into endless overheating. The atmosphere also affects sound and movement in strange ways. Because the air is so dense, sound would travel differently than on Earth, possibly carrying farther through the thick gas. Movement near the surface would feel heavy and slow because of the pressure surrounding everything. Even light behaves differently inside the dense atmosphere, scattering through the haze and creating a dim orange glow instead of clear skies. The deeper one descends into the atmosphere, the more isolated and trapped the environment becomes. Modern scientists continue studying Venus because the atmosphere still holds many unanswered questions. Researchers are investigating how the clouds maintain their structure, how superrotation works, and whether active volcanoes continue feeding gases into the atmosphere today. Some studies even explore whether microbial life could survive high in the upper cloud layers where temperatures are less extreme, though the acidic environment remains a major challenge for any form of life. These questions keep Venus scientifically important despite its deadly conditions. Future missions by NASA and the European Space Agency aim to return to Venus with better instruments and stronger technology. Scientists hope to study the atmosphere more closely and understand exactly how the runaway greenhouse catastrophe developed over time. New probes may survive longer than earlier missions, allowing deeper exploration of the atmosphere and surface. Some concepts even involve balloons floating within the upper atmosphere, where conditions are less destructive than the surface below. Yet no matter how advanced technology becomes, Venus remains one of the most difficult worlds ever visited by humanity. The atmosphere attacks spacecraft from the moment they arrive. Acid clouds corrode materials, violent turbulence shakes descending probes, temperatures climb towards levels capable of melting metal, and crushing pressure threatens every system. Even after landing successfully, the environment continues destroying machines minute by minute until communication finally ends. Every mission to Venus becomes a race against time inside a planet designed to destroy anything entering it. From orbit, Venus still looks calm and beautiful, glowing brightly beneath smooth clouds. But beneath those clouds lies an environment so extreme that it rewrote scientific understanding of planetary climates forever. The atmosphere of Venus is not just thick or hot. It is a complete planetary system driven into permanent catastrophe, where chemistry, pressure, heat, and weather combine into one endless hostile machine. What once looked like Earth's twin turned out to be a world hidden behind clouds so deadly that for centuries they concealed the most terrifying planet humanity had ever discovered. Scientists often describe Venus as a runaway greenhouse planet because the greenhouse effect there did not stop increasing until the entire planet became a permanent furnace. Understanding how Venus reached this state requires going back billions of years to the early history of the planet. Scientists believe Venus may once have looked very different from what it is today. Because Venus formed close to Earth and shares many similarities in size and composition, researchers think it may once have had large amounts of water on its surface. Ancient oceans may have covered parts of the planet billions of years ago when the Sun itself was younger and less powerful. At that time, Venus could have had more moderate temperatures and possibly a climate that allowed liquid water to remain stable for long periods. However, because Venus orbits closer to the Sun than Earth does, it received more solar energy from the beginning. Over immense spans of time, this extra heat slowly began pushing the planet toward instability. As temperatures increased, more water evaporated from the surface into the atmosphere. Water vapor itself is a greenhouse gas, meaning it traps heat very effectively. This created a dangerous cycle because more evaporation caused more warming, and more warming caused even more evaporation. Oceans that may once have covered parts of Venus slowly turned into atmospheric water vapor, thickening the heat-trapping effect around the planet. At first, this process may have been gradual, but eventually the system reached a tipping point where the warming accelerated uncontrollably. Scientists call this a runaway greenhouse effect because once it begins, the planet can no longer cool itself effectively. The atmosphere traps increasing amounts of heat while more and more water enters the air, feeding the process continuously. As the oceans disappeared into the atmosphere, another catastrophic process began. High above Venus, ultraviolet radiation from the Sun started breaking apart water molecules. Water is made of hydrogen and oxygen, and intense solar radiation separated these elements inside the upper atmosphere. The lightweight hydrogen atoms then escaped into space because Venus lacks a strong magnetic field capable of protecting the atmosphere effectively from solar wind. Over millions of years, enormous amounts of hydrogen drifted away into space permanently. This meant the water could never reform into oceans because one of its main components was literally being removed from the planet. The oxygen left behind likely reacted with rocks and surface minerals, while the hydrogen vanished forever. Venus slowly lost its water until the surface became completely dry. Once the oceans vanished, the climate system of Venus became even more unstable. On Earth, oceans help regulate temperature by absorbing heat and storing carbon dioxide through natural geological cycles. Venus lost this balancing system completely. Volcanoes may have released massive amounts of carbon dioxide into the atmosphere over long periods of time, and without oceans to absorb it, the gas accumulated continuously. The atmosphere thickened further, trapping even more heat until the entire planet transformed into a global oven. What remained was an atmosphere made mostly of carbon dioxide with crushing pressure and temperatures hot enough to melt metals. The planet had crossed a point where normal cooling processes could no longer function. The terrifying part about Venusian heat is not just how high the temperature becomes, but how stable it remains. On Earth, deserts cool at night because heat escapes into space after sunset. Venus does not behave this way because the atmosphere is too thick for rapid cooling. The heat becomes trapped and redistributed around the planet continuously by atmospheric circulation. Even the night side of Venus remains almost as hot as the side facing the Sun. The difference between day and night temperatures is surprisingly small, despite the planet's slow rotation. This means Venus never experiences relief from its own heat. Every region of the planet remains locked inside the same superheated environment. Venus also has no seasons like Earth because its axis tilt is very small. Earth experiences seasons because different parts of the planet receive varying amounts of sunlight throughout the year as the planet tilts during orbit. Venus does not tilt enough for strong seasonal changes to occur. Combined with the thick atmosphere spreading heat globally, this creates a world where temperatures remain almost permanently stable. The surface becomes a constant thermal environment with little variation across time or location. Whether standing near the equator or closer to the poles, the heat remains deadly. The atmosphere itself plays a major role in distributing this heat. Scientists studying Venus discovered that the thick atmosphere circulates energy around the planet extremely efficiently. Massive winds high above the surface move heat rapidly from one side of the world to the other. This atmospheric circulation prevents large temperature differences from developing between regions. The result is a planet where almost every location remains dangerously hot at all times. Infrared imaging from spacecraft helped scientists map these thermal patterns and revealed just how evenly the heat spreads across Venus. Infrared observations became one of the most important tools for studying Venus because visible light cannot penetrate the thick cloud layers properly. Infrared imaging allowed scientists to study temperature patterns and detect heat radiating through parts of the atmosphere. These observations confirmed that Venus maintains extreme temperatures globally rather than only in isolated regions. Infrared instruments also revealed details about atmospheric circulation and possible volcanic activity beneath the clouds. In some areas, scientists detected unusual thermal signatures suggesting that lava flows or active volcanic regions might still exist today. If true, This means Venus may continue producing internal heat through ongoing geological activity. The surface environment of Venus is so extreme that survival for any human being would be impossible without advanced protection, and even then survival would likely last only minutes. A human exposed directly to the surface would face instant overheating combined with crushing atmospheric pressure. The heat alone would rapidly destroy body tissues, while the pressure would compress the body with force similar to being deep underwater. Breathing would be impossible because the atmosphere contains almost no oxygen and is mostly carbon dioxide mixed with toxic gases. Even before these effects fully developed, the extreme temperature would begin destroying protective equipment almost immediately. A modern spacesuit designed for spacewalks around Earth would fail very quickly on Venus. Spacesuits are built mainly for vacuum and radiation protection, not for surviving inside an environment hotter than industrial furnaces. The external layers would begin overheating within moments of exposure. Cooling systems would struggle against the surrounding temperature because the environment itself is already far beyond normal operating limits. Joints and seals would weaken as heat transferred through the suit. Internal electronics would begin failing as temperatures rose beyond safe levels. Eventually, the suit would lose structural integrity, while the wearer inside faced fatal overheating and pressure exposure. Even robotic spacecraft struggled to survive on Venus for long periods. The Soviet Venera probes remain some of the greatest engineering achievements in planetary exploration because they were designed specifically to endure the heat and pressure of Venus for as long as possible. These spacecraft used thick pressure-resistant shells, cooling systems, and carefully protected electronics. Yet even the strongest of them survived only for limited periods on the surface before the environment destroyed them. The heat slowly penetrated every layer of insulation and protection until internal systems overheated completely. Some probes survived for less than an hour, while others lasted slightly longer before communication ended permanently. When a spacecraft descends toward Venus, the temperature outside rises steadily as it moves deeper into the atmosphere. At first, conditions may seem manageable in the upper cloud layers, but the deeper the probe falls, the more hostile the environment becomes. Heat builds continuously while pressure climbs higher with every kilometre. The atmosphere grows thicker and denser until the spacecraft feels less like it is falling through air and more like it is sinking into a hot ocean of gas. The exterior becomes surrounded by intense thermal energy, while the onboard systems fight desperately to stay alive. Inside the spacecraft, every system begins operating under stress. Cooling systems work constantly to prevent internal temperatures from rising too quickly. Electrical systems generate their own heat while also absorbing heat from outside. Lubricants inside moving mechanical parts begin thinning and boiling under the extreme temperatures. Metal structures expand as they absorb thermal energy, creating stress throughout the vehicle. Sensors exposed directly to the atmosphere begin failing one by one as the heat overwhelms them. Even before the spacecraft lands, Venus is already trying to destroy it. Once on the surface, the situation becomes even worse because the probe no longer moves through cooler upper layers of the atmosphere. It sits directly inside the hottest part of the environment. The ground itself radiates enormous heat into the surrounding air. Rocks and surface materials remain heated continuously under the thick atmosphere. Unlike Earth, where heat can escape after sunset, Venus traps thermal energy near the surface permanently. A lander sitting there becomes surrounded by heat from every direction at once. Scientists studying the Venera missions noticed that some spacecraft components warped slightly during operation because of the temperature stress. Internal electronics gradually failed as heat penetrated deeper into the vehicle over time. Cameras and communication systems weakened, while batteries lost efficiency under the extreme conditions. Eventually, the probes stopped transmitting altogether as the environment overcame every protective system humans had built into them. Venus did not destroy these spacecraft through explosions or sudden impacts. It killed them slowly through overwhelming heat and pressure. Mercury often surprises people because although it sits closer to the Sun, it is not hotter overall than Venus. Mercury lacks a thick atmosphere, so while the side facing the Sun becomes extremely hot during the day, the dark side cools dramatically at night. Venus behaves completely differently because its atmosphere traps and circulates heat continuously. The entire planet becomes an enclosed thermal system where heat cannot escape effectively. This is why Venus became the hottest planet in the solar system, despite receiving less solar energy than Mercury. Scientists continue studying how atmospheric circulation works on Venus because the planet distributes heat with incredible efficiency. Winds high above the surface race around the world, while lower layers remain dense and heavy. The atmosphere transfers energy constantly between regions, preventing major temperature differences from forming. Infrared studies showed that the clouds themselves also play a role by reflecting sunlight while trapping infrared radiation beneath them. This combination creates one of the most effective heat-trapping systems known in planetary science. Another disturbing aspect of Venusian heat is how it affects chemical reactions on the surface. Materials behave differently under such extreme conditions. Rocks may interact chemically with the atmosphere over long periods in ways rarely seen on Earth. Certain minerals become unstable under the intense heat and pressure. Scientists studying radar and infrared data believe parts of the surface may have been reshaped by volcanic activity relatively recently. Lava flows under Venusian conditions behave differently due to the thick atmosphere and high temperatures surrounding them. The atmosphere near the surface is so dense that heat transfer occurs very efficiently. On Earth, a person touching hot air briefly might survive because air is relatively thin and transfers heat slowly. On Venus, the dense atmosphere transfers heat far more aggressively. A human body exposed there would absorb thermal energy rapidly from the surrounding air itself. Even standing still would not reduce exposure because the atmosphere completely surrounds the body with superheated gas. The environment becomes deadly almost instantly. The sky on Venus would not appear bright blue like Earth's sky. Instead, thick clouds and atmospheric haze create a dim orange glow near the surface. Sunlight struggles to pass through the dense atmosphere and becomes scattered into dull, reddish tones. Visibility remains poor because the atmosphere absorbs and diffuses light continuously. Combined with the crushing heat, this creates an environment that feels enclosed and suffocating. A person standing there would see only distorted rocky terrain fading into thick orange haze while heat surrounds everything endlessly. Scientists also study Venus because it provides one of the clearest natural examples of what a runaway greenhouse effect can do to a planet. The process transformed a world that may once have held water into a permanently overheated environment. By studying Venus, researchers learn how atmospheres evolve and how climate systems can change under extreme conditions. This helps scientists understand not only Venus itself, but also the climates of planets around other stars. Many exoplanets discovered in recent years may experience similar greenhouse conditions. Modern missions continue preparing to return to Venus because many questions remain unanswered about its thermal systems and geological activity. NASA plans missions designed to study the atmosphere and surface in greater detail using improved instruments capable of surviving longer in extreme conditions. Scientists hope to understand exactly how the atmosphere circulates heat and whether active volcanoes still contribute to the planet's climate today. Better infrared imaging and atmospheric sensors may reveal processes hidden beneath the thick cloud cover. Even with improved technology, Venus remains one of the most dangerous destinations ever attempted in space exploration. Every spacecraft entering its atmosphere faces the same deadly combination of crushing pressure and overwhelming heat. Engineers must design systems capable of resisting temperatures that destroy ordinary electronics within minutes. Cooling systems must function inside an environment already hotter than many industrial furnaces on Earth. The challenge is not simply landing on Venus, but surviving there long enough to gather meaningful data before the planet destroys the spacecraft completely. The horror of Venusian heat comes from its permanence. The planet does not cool down after sunset. It does not experience changing weather capable of lowering temperatures significantly. The atmosphere traps and spreads heat endlessly across the entire world. Every rock, every cloud layer, every region of the surface exists inside the same thermal nightmare. What scientists discovered beneath the clouds was not just another hot planet, but a world transformed into a permanent planetary oven through runaway climate processes operating on a global scale. And as terrifying as the heat became, scientists soon realized the temperature was only part of the danger waiting below those clouds. The crushing atmosphere itself would become the next nightmare for every spacecraft descending toward the surface. Heat was only the beginning. Pressure that crushes steel. The heat on Venus is horrifying, but temperature alone is not what makes the planet so deadly. Long before a spacecraft can fully experience the burning surface, another force begins attacking it from every direction at once. The atmosphere of Venus is not thin and open like Earth's atmosphere. It is enormously heavy, dense, and violent in a way that changes how gases behave near the ground. At the surface, the atmospheric pressure reaches about 92 bars, which means the force pressing down on everything is around 92 times stronger than the air pressure humans experience on Earth. Scientists often compare this pressure to being nearly 1 kilometer underwater in Earth's oceans. That comparison alone reveals how extreme Venus really is, because deep ocean submarines on Earth require thick reinforced hulls just to survive those depths. Yet on Venus, that crushing force exists everywhere across the entire planet all the time. On Earth, people rarely think about atmospheric pressure because human bodies evolved to live comfortably inside it. The air around us presses against our skin constantly, but the pressure inside our bodies balances it naturally. On Venus, this balance becomes impossible because the external pressure is overwhelming. A human standing unprotected on the surface would experience instant disaster. The lungs would not function because the surrounding atmosphere would compress the chest with incredible force. Breathing would become impossible almost immediately, not only because the atmosphere lacks oxygen, but because the body itself could not expand properly against the crushing pressure outside. Every air-filled space inside the human body would be affected. The ears, lungs, and internal cavities would all experience severe compression, while the extreme heat attacked at the same time. The pressure on Venus changes the behavior of the atmosphere itself. Near the surface, the air becomes so dense that it no longer behaves like the invisible gas humans experience on Earth. Instead, it acts almost like a heavy fluid surrounding everything. Scientists often describe the lower Venusian atmosphere as behaving somewhere between a gas and a liquid, because of how thick and compressed it becomes. Movement through it would feel strange and heavy. Objects descending toward the surface encounter resistance, similar to moving through water instead of air. This dense atmosphere also transfers heat extremely efficiently, making the already deadly temperatures even more dangerous because thermal energy moves rapidly into anything exposed to the environment. When scientists first began studying Venus, they did not fully understand how severe the atmospheric pressure really was. Early observations from Earth could not measure the lower atmosphere accurately because the thick clouds blocked direct views of the surface. Some researchers expected high pressure, but few imagined conditions so extreme that ordinary spacecraft would be destroyed almost instantly. The truth only became clear when probes entered the atmosphere and started sending back measurements during descent. As the probes fell deeper through the clouds, pressure readings climbed continuously. Every kilometer downwards revealed a more hostile environment than expected. Instruments recorded crushing forces increasing until engineers realized Venus was not simply difficult to explore. It was one of the most mechanically destructive environments ever encountered. The deeper a spacecraft descends into Venus, the more dangerous the pressure becomes. In the upper atmosphere, conditions are still relatively manageable compared to the surface below. But as altitude decreases, the atmosphere thickens rapidly, the gas becomes denser and heavier while the pressure rises without stopping. By the time a probe approaches the surface, the environment outside pushes against the spacecraft with enormous force from every direction. Every panel, seal, wire, and connection experiences stress continuously. A single structural weakness can mean total destruction because the atmosphere exploits every flaw immediately. The Soviet Union became the first nation to truly confront this nightmare directly through the Venera program. These missions were among the most difficult engineering projects ever attempted in space exploration because the spacecraft had to survive conditions beyond anything experienced elsewhere in the solar system. Early Venera probes failed repeatedly. Some lost communication before reaching the surface. Others were crushed during descent as pressure overwhelmed their structures. Each failure forced Soviet engineers to redesign the spacecraft again and again, making them stronger, thicker, and more resistant to both heat and pressure. The engineers eventually realized that ordinary spacecraft construction methods were useless on Venus. Thin metal shells used for other space missions could not survive the lower atmosphere. The Venera probes needed reinforced structures capable of resisting pressure strong enough to crush steel. To achieve this, the spacecraft used heavy titanium pressure vessels designed like miniature deep-sea submarines. These shells surrounded the sensitive electronics inside and protected them from the atmosphere outside. Every opening, cable connection, and instrument mount had to be sealed carefully because even small weaknesses could fail under Venusian pressure. The Venera probes also carried cooling systems because heat and pressure worked together against the spacecraft. Pressure alone could crush the vehicle, while heat slowly cooked the electronics inside. Engineers used insulation and cooling mechanisms to delay the inevitable destruction long enough for the probes to send back data. Even with these protections, survival times were short. Some probes survived only minutes after landing. Others lasted slightly longer, transmitting precious information back to Earth before finally going silent forever. One of the most terrifying aspects of the Venus missions was how slowly the destruction happened. The spacecraft did not always explode dramatically. Instead, the environment killed them piece by piece. Internal temperatures rose steadily while the atmosphere pushed constantly against the hull. Mechanical systems weakened. Electronics overheated. Communication signals became unstable. Eventually, the probes stopped transmitting entirely as Venus overwhelmed every protective system humans had built into them. The silence after those final transmissions became part of the legend surrounding the Venera missions. Scientists studying the data from these missions realized that the Venusian atmosphere near the surface behaves in ways unfamiliar to normal human experience. Because the atmosphere is so dense, aerodynamic effects become very different from those on Earth. A descending probe moves through thick compressed gas that creates strong drag forces. Wind behaves differently near the surface because the heavy atmosphere slows movement despite the violent upper atmospheric winds higher above. Sound would also travel differently through this dense environment. Noise could potentially carry farther and more efficiently than on Earth because the atmosphere itself is thicker and better at transmitting vibrations. The pressure affects every material differently. Metals expand under the intense heat while simultaneously being compressed by the atmosphere outside. Mechanical joints experience enormous stress. Lubricants inside moving systems begin failing because high temperatures and pressure change their chemical behavior. Rubber seals harden or weaken. Electrical systems become unstable as protective insulation deteriorates. Every component inside a spacecraft must survive conditions that push materials close to their physical limits. The comparison to deep ocean pressure on Earth helps explain why Venus is so dangerous mechanically. Deep-sea submarines on Earth require thick pressure-resistant hulls because water is heavy and compresses strongly at depth. If a submarine hull fails far underwater, the surrounding pressure crushes the vessel instantly. On Venus, spacecraft face a similar situation, except they are not underwater. The atmosphere itself creates the crushing force. A probe landing on Venus essentially enters an ocean made of superheated carbon dioxide gas. The atmosphere near the surface is so thick that even simple movement becomes difficult. If a human somehow stood there with impossible protection against the heat and pressure, moving through the atmosphere would feel heavy and unnatural. The dense gas would resist motion more strongly than Earth's air. Dust and particles would behave differently because the atmosphere carries them slowly through the compressed environment. Visibility would remain poor due to thick haze and scattering light, making the surface feel enclosed and claustrophobic. When the first successful Venera probes finally reached the surface and transmitted images, scientists were shocked not only by the rocky landscape, but by the realization that these machines were operating inside pressure conditions once thought nearly impossible for electronics to survive. The probes showed flat, rocky terrain beneath an orange sky while their internal systems slowly approached failure. Cameras functioned briefly, while temperature and pressure readings confirmed the full horror of the environment. Every second those spacecraft survived became a triumph of engineering against one of the harshest environments in the solar system. The Soviet engineers behind the Venera program achieved what many believed impossible at the time. Missions like Venera 7 became the first spacecraft to successfully land on another planet and send data back from the surface. Later, missions improved survival times and image quality. Venera 9 returned the first surface photographs from Venus, while Venera 13 survived long enough to send color images and detailed scientific measurements. These missions remain some of the greatest achievements in robotic space exploration because they succeeded inside conditions designed to destroy machines. The data collected by these probes confirmed that the pressure on Venus remained stable across the surface. Unlike Earth, where weather systems create changing atmospheric conditions, Venus maintains crushing pressure almost everywhere because of its enormous atmosphere. There are no regions where humans could land safely without protection. The entire planet exists beneath the same heavy blanket of compressed gas. Even elevated regions on Venus still experience pressure far beyond anything humans can survive naturally. Scientists also discovered that the pressure contributes to the strange thermal behavior of Venus. The dense atmosphere traps heat efficiently because compressed carbon dioxide absorbs and redistributes thermal energy extremely well. Heat does not escape easily into space. Instead, it remains locked inside the atmosphere and circulates around the planet continuously. This combination of pressure and greenhouse heating transformed Venus into a stable furnace world, where conditions remain deadly day and night. Infrared studies and radar mapping later revealed more about how the lower atmosphere behaves. Researchers observed that the dense atmosphere near the surface interacts strongly with the landscape itself. Mountains, valleys, and volcanic plains influence atmospheric flow patterns despite the thick haze. Some studies suggest pressure waves and atmospheric disturbances move through the dense lower layers differently than weather systems on Earth. The atmosphere behaves almost like a massive moving ocean surrounding the planet. The psychological horror of Venusian pressure comes from the idea that the environment itself attacks constantly from every direction. Heat burns from outside, while pressure crushes inward simultaneously. There is no open air, no relief, and no safe region once descending deep enough into the atmosphere. A spacecraft entering Venus becomes trapped inside a steadily tightening environment where survival time decreases with every kilometre downward. Inside the Venera landers, engineers monitored how quickly conditions were overwhelming the probes. Internal temperatures slowly climbed despite cooling systems. Electrical resistance changed as components heated up. Structural stresses increased while communication systems struggled to remain stable. Some transmissions became weaker before ending entirely. Scientists listening to the final signals from these probes understood they were hearing machines dying inside another world. One reason Venusian pressure is so destructive is because of the sheer mass of the atmosphere above the surface. On Earth, the atmosphere is relatively thin compared to the size of the planet. Venus, however, possesses an atmosphere so massive that the weight of the gas itself creates crushing conditions below. Every square centimetre of the surface sits beneath enormous atmospheric mass, pressing downward continuously. This creates a stable, high-pressure system unlike anything humans experience naturally. The clouds above Venus hide this reality completely from space. From orbit, the planet appears smooth and calm beneath pale yellow cloud layers. There are no visible signs of the crushing force below. A spacecraft approaching Venus might appear to be descending into an ordinary atmosphere at first. Only during descent do the true conditions reveal themselves. Instruments begin recording rising pressure while the external environment grows denser and hotter. The calm appearance from space slowly transforms into mechanical horror. The pressure also changes how parachutes and descent systems work. On Earth, parachutes slow spacecraft effectively because the atmosphere provides resistance against falling motion. On Venus, the dense lower atmosphere creates enormous drag forces. Early during descent, parachutes work efficiently, but deeper down the atmosphere becomes so thick that descent systems must adapt carefully. Engineers designing Venus landers had to account for the strange aerodynamic behaviour caused by the dense compressed atmosphere. Another major challenge involves maintaining seals around scientific instruments. Any opening exposed to Venusian pressure becomes a possible failure point. Cameras, sensors and sampling equipment require protective systems capable of operating without allowing the atmosphere to penetrate sensitive internal areas. Even small leaks become catastrophic because the pressure difference forces hot gas inward aggressively. Designing equipment for Venus requires solving problems far beyond those faced by most other planetary missions. The crushing environment near the surface also affects chemical reactions and material stability. Certain materials weaken faster under combined heat and pressure. Electronics designed for Earth fail rapidly because their components cannot handle such conditions. Modern research into Venus exploration includes developing entirely new types of electronics capable of operating at much higher temperatures and pressures without traditional cooling systems. Scientists hope future technology may allow longer missions on the surface. Despite decades of research, Venus still remains one of the hardest places in the solar system to explore directly. Mars receives far more attention because humans may one day walk there. Venus presents a completely different challenge because survival itself becomes nearly impossible. The pressure alone requires engineering solutions closer to deep ocean exploration than normal spacecraft design. Every mission to Venus becomes a battle against one of the most mechanically hostile environments known. Scientists continue studying Venus because understanding its atmosphere helps explain planetary evolution and climate systems across the universe. Many exoplanets discovered around distant stars may experience similar runaway greenhouse conditions and extreme atmospheric pressures. Venus serves as a real example of what happens when planetary climate systems spiral into permanent overheating beneath a massive atmosphere. By studying it, researchers gain insight into how worlds change over time. Modern space agencies still plan future missions to Venus despite the danger. NASA and other agencies are developing new probes capable of surviving longer in the crushing atmosphere. Some mission concepts involve balloons floating high in the upper atmosphere, where pressure and temperature are less extreme. Others aim to place advanced landers on the surface using improved heat-resistant electronics and stronger structural materials. Engineers continue pushing technology forward in hopes of extending survival times beyond the short lives of earlier probes. Yet the reality remains terrifyingly clear. Venus is a planet where the atmosphere itself becomes a weapon. The pressure crushes, compresses, and destroys continuously. Spacecraft entering the lower atmosphere face forces strong enough to collapse poorly designed structures instantly. Human bodies would fail within moments. Even the strongest robotic probes survive only briefly before the planet overwhelms them completely. The Venera missions proved that humanity could touch the surface of Venus, but they also proved how deadly that achievement truly was. And even after surviving the heat and pressure, another danger waited hidden inside the clouds above and the toxic chemistry surrounding the planet. Even if you survived the pressure, Venus still had more ways to kill you. The rain that never reaches the ground. A spacecraft entering the atmosphere of Venus would not fall through ordinary clouds. It would descend into a chemical nightmare hanging above the planet, like a poisoned ocean in the sky. From orbit, the clouds of Venus look smooth and bright, reflecting sunlight so strongly that the planet shines like a white beacon in space. But inside those clouds is an environment so hostile that even machines struggle to survive it for long. These are not water clouds like the ones floating above Earth's oceans. They are made mostly of sulfuric acid, one of the most corrosive substances found naturally in planetary atmospheres. Every layer of the Venusian sky is filled with acid droplets drifting through thick yellow haze, creating a world where the atmosphere itself behaves like a weapon. Long before any spacecraft reaches the burning surface below, it must first survive a journey through clouds capable of eating away at metal, damaging electronics, and surrounding the probe with toxic chemistry from every direction. The sulfuric acid clouds of Venus begin forming high in the atmosphere where sunlight interacts with gases released into the air. The process starts mainly with sulfur dioxide, a gas believed to come partly from volcanic activity on the surface. Venus may still contain active volcanoes today, and even ancient volcanic eruptions could have released enormous amounts of sulfur compounds into the atmosphere over millions of years. Once sulfur dioxide rises into the upper atmosphere, it mixes with tiny amounts of water vapor and becomes exposed to intense ultraviolet radiation from the sun. The sunlight drives chemical reactions that transform the sulfur dioxide into sulfuric acid molecules. These molecules then combine into microscopic droplets that gather together and spread through the cloud layers surrounding the planet. This process never truly stops because the atmosphere of Venus is constantly moving. Winds carry sulfur compounds around the globe, while sunlight continuously powers chemical reactions in the upper atmosphere. Over time, this creates enormous cloud systems stretching across the entire planet. Scientists discovered that the clouds form several thick layers, reaching from high altitudes deep into the atmosphere below. The upper cloud decks are brighter and more reflective because they interact directly with sunlight. Deeper layers become darker and denser, filled with thick haze and drifting acid particles. Together, they create a permanent global shield hiding the surface from view. Inside these clouds, sulfuric acid droplets exist almost everywhere. A spacecraft descending into the atmosphere enters a region filled with corrosive liquid particles floating through the air. These droplets vary in size from tiny aerosols to larger formations capable of combining into acid rain. The environment becomes chemically aggressive because sulfuric acid attacks many materials directly. Protective coatings weaken. Metals corrode over time. Sensitive equipment requires heavy shielding simply to survive exposure during descent. Even then, Venus slowly damages the spacecraft every second it remains inside the atmosphere. The terrifying part is that Venus actually has rain, but it is not rain in the way humans understand it on Earth. High above the surface, sulfuric acid droplets combine into larger drops and begin falling downward through the atmosphere. For a moment, it resembles rainfall, but as the droplets descend deeper into the hotter lower atmosphere, temperatures rise so dramatically that the acid begins evaporating before it can ever reach the ground. The rain disappears in mid-air, turning back into vapor long before touching the surface. Scientists sometimes describe this as phantom rain, because the process begins like normal rainfall but never completes itself. The planet creates storms that erase themselves before reaching the ground below. If a human somehow floated inside those clouds without protection, survival would be impossible. Sulfuric acid is extremely dangerous to living tissue because it rapidly destroys organic material through chemical reactions. Breathing inside the Venusian atmosphere would immediately burn the lungs and airways. Eyes and skin would suffer severe chemical damage almost instantly. Even tiny acid droplets drifting through the air would become lethal when inhaled. Combined with the intense heat and pressure already present on Venus, the clouds transform the atmosphere into one of the most toxic environments known in the solar system. The deeper a spacecraft travels through the clouds, the stranger the environment becomes. Sunlight weakens inside the thick haze, turning the atmosphere dark yellow and orange. Visibility drops dramatically because light scatters through billions of drifting acid particles. A probe descending through the atmosphere would see endless clouds stretching in every direction, while instruments continuously monitor rising heat and pressure. The outside of the spacecraft would slowly collect corrosive residue from the acid droplets while winds shake the vehicle during descent. Every kilometer downward feels like entering a deeper level of a planetary storm system designed to destroy anything inside it. Scientists studying Venus noticed that the clouds move with incredible speed high above the planet. Winds in the upper atmosphere race around Venus far faster than the planet rotates itself. This process, called atmospheric superrotation, creates enormous circulation patterns carrying heat and chemicals around the globe continuously. Sulfuric acid clouds move through these atmospheric rivers, while sunlight drives chemical reactions across the planet. The atmosphere never truly rests. Clouds shift, gases circulate, and chemical cycles continue endlessly above the burning surface below. The chemistry inside the clouds remains one of the most complicated parts of Venusian science, because the atmosphere behaves very differently from Earth's. On Earth, clouds mainly involve water vapor condensing into droplets due to temperature changes. Venus operates on entirely different chemistry dominated by sulfur compounds and carbon dioxide. Scientists believe volcanic activity may constantly feed sulfur dioxide into the atmosphere from below. Once exposed to sunlight in the upper atmosphere, the gas transforms through photochemical reactions into sulfuric acid. Some of this acid later breaks apart again under changing conditions, continuing a giant atmospheric cycle powered by solar radiation and atmospheric circulation. One of the most disturbing discoveries about Venus is that the clouds may contain electrical activity similar to lightning storms. Several missions detected signals that strongly suggest lightning flashes inside the atmosphere. If true, this means electrical storms may form inside giant sulfuric acid cloud systems moving through a superheated atmosphere. Unlike thunderstorms on Earth, which form mainly from water clouds and ice particles, Venusian storms would involve completely different chemistry and atmospheric behavior. Imagine lightning flashing inside toxic acid clouds while corrosive droplets drift through hurricane-force winds high above the planet. The atmosphere of Venus turns weather itself into something alien and hostile. Spacecraft descending into this environment face constant danger from corrosion. Engineers designing Venus missions had to account not only for heat and pressure, but also for chemical damage caused by the clouds. Some materials weaken rapidly when exposed to sulfuric acid. Electronic systems require sealed protection against corrosive particles entering sensitive components. Camera lenses, sensors, and communication equipment must survive acid exposure long enough to gather data before the atmosphere destroys them. Every Venus mission becomes a race between scientific exploration and environmental destruction. The Soviet Venera missions remain among the greatest examples of engineering against impossible conditions. As the probes descended through the clouds, instruments measured temperature, pressure, atmospheric composition, and chemical conditions continuously. The spacecraft entered thick haze filled with sulfuric acid droplets, while turbulence shook the descent systems. Protective shells shielded the internal electronics, while the atmosphere outside became hotter and denser. Some probes survived only briefly after landing because Venus attacked them through every possible environmental force at once. Yet before dying, these spacecraft revealed the terrifying reality hidden inside the clouds. One reason Venus appears so bright from Earth is because its cloud layers reflect enormous amounts of sunlight back into space. The sulfuric acid clouds act like a giant mirror surrounding the planet. Sunlight strikes the upper atmosphere and scatters outward, making Venus the brightest planet visible in Earth's sky after the Moon. For centuries, this brightness helped hide the truth beneath the clouds, because observers could not see through the reflective atmosphere. What looked beautiful from space concealed one of the harshest environments humans had ever discovered. Scientists still debate some of the deeper mysteries hidden within the clouds, because Venus refuses to fully explain itself even after decades of study. One of the biggest mysteries involves something called the unknown ultraviolet absorber. When researchers studied Venus in ultraviolet light, they noticed dark patterns inside the clouds absorbing more radiation than expected. Something in the atmosphere was blocking ultraviolet light strongly, but scientists could not fully identify the chemical responsible. Several theories exist, including unusual sulfur compounds, chlorine compounds, or complex chemical particles not yet fully understood. This unknown absorber became one of the strangest mysteries in planetary science because it suggests Venusian cloud chemistry may be more complicated than originally believed. Some scientists propose that unknown reactions inside the clouds could be producing exotic chemical substances unlike anything common on Earth. Others wondered whether microscopic particles or unusual mineral compounds might drift through the atmosphere. The dark ultraviolet patterns move with atmospheric circulation, changing shape over time like giant chemical shadows floating through the clouds. The possibility of strange chemistry inside the atmosphere became even more interesting when some researchers considered whether the upper cloud layers might contain conditions less deadly than the surface below. High above the crushing heat near the ground, temperatures and pressures become somewhat closer to those found on Earth. Even though the clouds remain highly acidic, scientists discovered that some microorganisms on Earth can survive surprisingly harsh acidic environments. This led to discussions about whether microbial life could theoretically survive in the upper Venusian atmosphere. No evidence confirms life exists there, but the idea added another layer of mystery to the planet's cloud systems. Despite this scientific curiosity, the clouds remain overwhelmingly hostile. The sulfuric acid concentration alone creates severe challenges for any form of life. Combined with ultraviolet radiation, chemical instability, and atmospheric turbulence, Venus remains one of the most difficult places imaginable for biology. Yet the strange chemistry inside the clouds continues attracting researchers because the atmosphere still behaves in ways not fully understood. As spacecraft descend deeper below the cloud layers, the atmosphere changes gradually from corrosive haze into dense superheated gas. The acid rain disappears before reaching the surface because temperatures become too high for liquid sulfuric acid to survive. This creates a strange transition zone where droplets evaporate while descending, leaving behind thick toxic vapor. A probe falling through this region would witness clouds fading into orange haze while the environment grows darker, hotter, and heavier. Instruments would register increasing pressure while corrosive chemicals coat the exterior surfaces. The atmospheric circulation of Venus keeps these cloud systems active continuously. Winds carry sulfur compounds across the planet while heat rises and falls through different atmospheric layers. Scientists studying radar and infrared observations discovered that the clouds move in massive rotating systems surrounding the entire planet. Some cloud structures stretch thousands of kilometers across the atmosphere. Patterns shift and evolve over time, while chemical reactions continue endlessly under sunlight. The atmosphere also influences how light behaves on Venus. Sunlight entering the cloud layers scatters repeatedly through acid particles, creating the pale yellow appearance seen from orbit. Deeper down, light weakens and turns orange as the atmosphere absorbs different wavelengths. Near the surface, visibility becomes poor because the thick atmosphere diffuses light in every direction. Shadows would appear weak and blurry, while distant objects fade into haze quickly. Combined with the crushing heat and pressure, the dim orange atmosphere creates a world that feels enclosed and suffocating. Researchers continue using infrared imaging and spectroscopy to study the cloud chemistry in greater detail. These tools allow scientists to examine how different gases absorb and emit radiation inside the atmosphere. By studying these patterns, researchers identify sulfur compounds, trace gases, and temperature structures within the cloud layers. Some studies suggest that volcanic eruptions may still release sulfur dioxide into the atmosphere today, helping maintain the sulfuric acid cloud systems. If Venus remains volcanically active, then the planet may still be feeding fresh chemicals into its atmosphere continuously. Modern missions planned by NASA and the European Space Agency aim to study these mysteries more closely. Future probes may descend through the clouds using improved instruments capable of analyzing atmospheric chemistry in greater detail than earlier missions. Scientists hope to identify the unknown ultraviolet absorber and understand how atmospheric circulation shapes the cloud systems over time. Some mission concepts even involve floating balloons designed to operate inside the upper atmosphere, where conditions are less extreme than the surface below. The engineering challenges remain enormous because Venus attacks spacecraft through chemistry as well as heat and pressure. Protective coatings must resist acid corrosion. Scientific instruments require sealed compartments capable of surviving both chemical exposure and thermal stress. Descent systems must endure turbulence inside thick cloud layers while maintaining communication with orbiting spacecraft and Earth. Every mission to Venus becomes a battle against one of the most chemically aggressive environments known. What makes the clouds of Venus truly terrifying is how deceptive they appear from a distance. From Earth, Venus shines beautifully in the night sky. Through telescopes, the cloud layers look smooth and calm. Nothing visible from space reveals the chemical violence hidden inside them. But beneath that bright reflective shell is an atmosphere filled with sulfuric acid droplets, toxic storms, crushing pressure, and temperatures capable of melting metal. The clouds are not protecting the planet. They are trapping it inside a permanent environmental catastrophe. A spacecraft descending through those clouds enters a world where every layer becomes more hostile than the last. Acid coats the exterior while visibility fades into thick yellow haze. Instruments register rising heat and pressure while atmospheric turbulence shakes the vehicle during descent. Lightning may flash somewhere inside the clouds while corrosive droplets drift through the air. Then the rain begins to fall, only to vanish again before touching the surface below. Venus creates storms that destroy themselves in mid-air because even the rain cannot survive the world beneath it. And deeper below those poison clouds, beyond the acid storms and chemical haze, the surface waits under darkness and crushing heat, ready to destroy anything that survives the descent. The winds of Venus. From space, Venus looks calm. Its clouds appear smooth, pale, and almost peaceful, like thick layers of cream wrapped around the planet. Nothing about it suggests motion or violence. But that calm appearance is one of the biggest lies in the solar system, because hidden inside those clouds is one of the strangest and most powerful atmospheric systems ever discovered. The atmosphere of Venus does something scientists still struggle to fully explain, even after decades of research. The entire atmosphere moves faster than the planet itself. The world below turns painfully slowly while the sky above races around it at terrifying speed. Imagine standing on a planet where the ground barely moves beneath your feet, yet the entire atmosphere screams overhead like a giant storm system wrapping around the world. That is Venus. The planet rotates so slowly that one full Venus day lasts about 243 Earth days. Yet the upper atmosphere circles the entire planet in only around 4 Earth days. The sky itself moves faster than the world underneath it. This phenomenon is called atmospheric superrotation and it remains one of the greatest mysteries in planetary science. On Earth, the atmosphere moves because of heat differences, ocean currents, and the rotation of the planet itself. Winds exist, storms form, jet streams move across continents, but the atmosphere generally follows the planet's rotation. Venus behaves completely differently. Its atmosphere has somehow broken free from the slow turning of the surface below. High above the ground, winds race around the planet at speeds reaching 300 to 400 kilometers per hour. Entire cloud systems circle Venus again and again, while the surface beneath them barely turns at all. It is like watching a hurricane spin around a motionless world endlessly. The first hints of this strange behavior appeared when scientists began studying the movement of Venusian clouds through telescopes and spacecraft observations. Researchers noticed that cloud patterns change position far too quickly to match the slow rotation of the planet itself. At first, this seemed impossible because there was no clear reason why the atmosphere should move so much faster than the surface. But as more data arrived from missions studying Venus, the truth became undeniable. The atmosphere was rotating independently, driven by forces scientists did not yet fully understand. One reason this discovery shocked researchers was because Venus already behaved strangely in other ways. The planet rotates backward compared to most worlds in the solar system, meaning the sun rises in the west and sets in the east. Its rotation is also incredibly slow. A single Venus day lasts longer than a Venus year. The planet takes about 225 Earth days to orbit the sun, yet it takes even longer to complete one rotation on its axis. This means a person standing on the surface would experience an incredibly slow passage of time between sunrises. The surface itself almost feels frozen in motion. Yet above that nearly motionless ground, the atmosphere races continuously. The upper atmosphere of Venus is where the most violent winds exist. At altitudes around 60 to 70 kilometers above the surface, thick sulfuric acid clouds race around the planet in powerful atmospheric currents. These winds move so fast that they can circle Venus in just a few Earth days. Entire cloud systems stretch across thousands of kilometers while moving at speeds stronger than many hurricanes on Earth. A spacecraft floating in these upper layers would experience constant atmospheric motion, surrounded by thick yellow clouds racing through the sky. Scientists studying these winds discovered that the atmosphere behaves like a giant spinning machine, powered by solar energy and atmospheric circulation. Sunlight heats the upper atmosphere unevenly, creating temperature differences that help drive motion through the clouds. But that alone does not fully explain the incredible speeds observed on Venus. Researchers believe several different processes work together to maintain the superrotation. Atmospheric waves, heat transfer, turbulence, and pressure differences may all contribute to keeping the atmosphere moving faster than the planet itself. The deeper scientists looked into the atmosphere, the stranger it became. Venus does not have weather systems exactly like Earth's weather systems. There are no oceans feeding giant water storms. There are no seasons driving major temperature changes because Venus has almost no axial tilt. Yet the atmosphere remains active and violent in its own way. Giant circulation cells move heat around the planet continuously. Thick cloud layers churn through powerful wind systems while turbulence ripples through the atmosphere. The entire planet feels wrapped inside a global storm structure that never truly stops moving. One of the most fascinating parts of Venusian weather involves atmospheric waves. These are enormous wave-like disturbances moving through the atmosphere, somewhat similar to waves moving across water. Scientists observed huge stationary wave structures in the clouds, especially above mountainous regions on the surface. Some atmospheric waves stretch for thousands of kilometers across the sky. They form when winds moving through the dense atmosphere interact with mountains and terrain below, sending energy upward into the cloud layers. These giant waves ripple through the atmosphere in patterns visible from orbit. The atmosphere near the surface behaves differently from the upper cloud layers. High above the planet, winds move at incredible speed, but near the ground, the dense atmosphere slows dramatically. On the surface itself, winds are surprisingly weak compared to the violent upper atmosphere. A person standing there would not experience hurricane-force winds pushing against them directly. Instead, the thick atmosphere would move more slowly, heavy, and dense like a hot fluid surrounding the body. The strange contrast between the calm lower atmosphere and the violent upper clouds creates one of the most unusual weather systems in the solar system. Even though surface winds are slower, the dense atmosphere still carries enormous force because the air itself is so thick. A gentle breeze on Venus can move dust and small particles effectively because the atmosphere is much denser than Earth's air. Scientists studying surface images from Soviet landers noticed signs that wind still shapes parts of the terrain despite the slower movement near the ground. Dust streaks, surface deposits, and weathered rocks suggest atmospheric motion continues, influencing the landscape over long periods of time. The cloud layers themselves move in giant bands around the planet. From orbit, spacecraft observed swirling structures, dark streaks, bright cloud regions, and changing atmospheric patterns moving continuously through the upper atmosphere. Some cloud formations resemble giant storms larger than entire countries on Earth. Others appear as long atmospheric rivers circling the globe. The movement never stops. The clouds race endlessly around the planet while sunlight reflects off the upper atmosphere, making Venus appear bright and smooth from far away. Inside the atmosphere, turbulence creates another level of danger for spacecraft descending toward the surface. As probes fall through the clouds, they experience shifting wind speeds and atmospheric instability. The atmosphere does not behave like calm air. It churns and moves unpredictably in places, especially where atmospheric layers interact with one another. Some descent probes experience shaking and vibration while falling through different cloud regions. Turbulence combined with thick haze and acid droplets turned every descent into a dangerous journey through an alien storm system. The Soviet Venera probes provided some of the first direct measurements of Venusian winds. As the spacecraft descended through the atmosphere, instruments recorded wind speeds, turbulence levels, temperature changes, and atmospheric density. The data revealed just how dynamic the atmosphere really was. High-altitude winds moved extremely fast, while deeper layers became slower and denser. These measurements helped scientists build the first detailed models of atmospheric circulation on Venus. One of the most famous discoveries came from tracking cloud movements using ultraviolet imaging. Scientists noticed dark streaks and patterns inside the upper clouds moving rapidly around the planet. These features helped researchers measure wind speeds directly by observing how fast cloud structures traveled over time. The results confirmed that the atmosphere circles Venus far faster than the planet rotates itself. Even today, spacecraft continue studying these cloud motions to understand the mechanics behind superrotation. The giant weather systems on Venus operate on a planetary scale. Earth experiences local storms, hurricanes, and jet streams, but Venus behaves more like one enormous connected atmospheric machine. Heat absorbed from sunlight enters the upper atmosphere and becomes distributed through global circulation patterns. Winds carry energy continuously around the world, while thick clouds trap heat below. The entire atmosphere functions as a single interconnected system, stretching from the upper cloud layers down to the superheated surface. Scientists believe heat plays a major role in driving the superrotation. The sun heats the atmosphere unevenly between the day side and night side of the planet, creating thermal tides inside the atmosphere. These tides behave somewhat like waves caused by heating rather than gravity. As the atmosphere expands and contracts due to solar heating, momentum transfers through the cloud layers. Combined with planetary rotation and atmospheric circulation, this may help maintain the rapid winds observed in the upper atmosphere. Another important factor involves vertical atmospheric motion. Heat rising from lower layers may transfer energy upward into the cloud decks, where faster winds dominate. Some researchers believe momentum from atmospheric waves becomes trapped and amplified in certain regions, accelerating the upper atmosphere over time. Others focus on turbulence and interactions between different atmospheric layers. Even with modern computer models and decades of study, scientists still do not fully understand why Venus developed such extreme superrotation while Earth did not. This mystery makes Venus scientifically important because understanding atmospheric superrotation may help explain weather systems on other planets as well. Some exoplanets orbiting distant stars may experience similar atmospheric behavior under thick atmospheres and intense heating. By studying Venus, researchers gain insight into how atmospheres evolve under extreme conditions. The planet becomes a natural laboratory for understanding atmospheric physics on a scale impossible to recreate on Earth. The visual appearance of Venusian winds from orbit is haunting. Spacecraft images show clouds racing around the planet in long curved bands while the surface below remains hidden beneath thick haze. Dark ultraviolet markings shift through the atmosphere like giant shadows moving across a boiling sky. The upper atmosphere appears alive with motion while the planet itself rotates slowly beneath it. This contrast creates one of the strangest scenes in the solar system. The world below feels trapped and motionless, while the sky above never stops moving. If a human somehow floated high in the upper atmosphere, the experience would be unlike anything on Earth. Thick yellow clouds would surround the observer, while powerful winds carried the atmosphere around the planet at enormous speed. Visibility would change constantly as haze moved through the sky. The sun would appear dim and distorted behind the cloud layers. Turbulence would shake the surrounding atmosphere, while sulfuric acid droplets drifted through the air. The sky itself would feel unstable and violent, even without visible storms like those on Earth. Closer to the surface, the atmosphere becomes heavier and slower, but the sense of isolation grows stronger. The thick, dense air scatters light and muffles visibility. Above, giant cloud systems race overhead far faster than the ground itself moves. A person standing there would experience one of the strangest contradictions imaginable. The sky would be in violent motion while the surface remained almost still beneath it. The atmosphere also distributes heat extremely efficiently across Venus. Because the winds move energy around the planet so effectively, temperatures remain surprisingly similar between day and night regions. On Earth, deserts cool rapidly after sunset because heat escapes into space. Venus does not allow this. The atmosphere traps heat while circulating it globally, preventing major temperature differences from developing. The result is a world where the entire atmosphere functions like a giant rotating oven. Modern missions continue studying these atmospheric systems in detail. Orbiters equipped with infrared cameras, ultraviolet imaging systems, and atmospheric sensors monitor cloud movement continuously. Scientists track wind speeds, wave patterns, and temperature structures across the planet. Some missions focus specifically on understanding how atmospheric superrotation forms and survives over long periods. Others investigate how the cloud chemistry interacts with atmospheric circulation. Future missions planned by NASA and the European Space Agency may send advanced probes and balloons into the atmosphere itself. Floating platforms inside the upper cloud layers could study wind systems directly for extended periods of time. Because temperatures and pressures are less extreme high above the surface, scientists believe long-duration atmospheric missions may become possible there before successful long-term surface missions. The engineering challenges remain enormous, because the atmosphere of Venus combines powerful winds, acid clouds, extreme heat, and crushing pressure into one continuous system. Any spacecraft entering the atmosphere must survive turbulence, corrosive chemicals, and shifting atmospheric conditions during descent. Communication systems must function through dense cloud layers while instruments collect data inside violent atmospheric currents. Every mission becomes a fight against one of the most hostile weather systems in the solar system. What makes the winds of Venus truly terrifying is not just their speed, but their scale. These are not isolated storms crossing continents. The entire atmosphere is moving. Massive cloud systems wrap around the whole planet while giant atmospheric waves ripple through the sky. Heat, turbulence, and chemical reactions combine into a global machine powered by sunlight and trapped beneath thick clouds. Venus turned its entire atmosphere into a planetary engine that never stops spinning. From a distance, Venus still looks peaceful. The clouds appear smooth and beautiful under sunlight. But hidden inside them are winds powerful enough to circle the world in days, while the planet itself barely rotates underneath. The sky races endlessly above a motionless surface trapped under crushing pressure and burning heat. Every layer of the atmosphere moves with strange and violent energy that scientists still struggle to fully explain. And beneath those racing clouds, hidden under the choking haze and endless atmospheric motion, lies a surface waiting in silence beneath one of the most violent skies ever discovered. Landscape of a dead world. The surface of Venus is one of the most terrifying places humans have ever discovered in the solar system. Beneath the thick yellow clouds, beneath the sulfuric acid storms, beneath the violent atmosphere racing around the planet, lies a world that looks less like a planet and more like the remains of a global disaster that never ended. Nothing moves naturally across the surface except slow atmospheric currents and possible volcanic activity deep below the crust. There are no oceans, no rivers, no rain reaching the ground, no signs of life, and no relief from the crushing environment. The land stretches endlessly in every direction as a burning desert of volcanic rock under dark orange skies. Mountains rise from giant lava plains while impact craters scar the terrain like wounds frozen in time. Every part of the landscape feels ancient, overheated, and hostile. The atmosphere above is so thick that sunlight barely reaches the ground properly, turning the surface into a dim world trapped under permanent haze. If a human stood there, the experience would feel less like standing on another planet and more like being trapped inside a giant industrial furnace that extends across an entire world. For centuries, nobody knew what the surface of Venus actually looked like because the planet hides itself behind clouds so dense that visible light cannot penetrate them. Ordinary telescopes showed only a bright white sphere with swirling cloud patterns. Scientists could not see mountains, valleys, or plains beneath the atmosphere because human eyes and standard cameras were effectively blind to the surface. This mystery allowed imagination to fill the gap. During the late 19th and early 20th centuries, many researchers believed Venus might be covered in jungles, swamps, or giant oceans hidden beneath the clouds. Some artists painted the planet as a prehistoric world filled with thick vegetation and dinosaur-like creatures living under endless cloud cover. Others imagined steaming rainforests or giant tropical seas. The reality turned out to be far more horrifying. The truth about the Venusian surface only began emerging when radar technology improved during the 20th century. Radar changed everything because, unlike visible light, radar waves could penetrate the thick atmosphere and bounce off the ground below. Scientists on Earth began sending radar signals toward Venus and measuring the reflections returning from the surface. Slowly, rough maps started forming. Hidden beneath the clouds was not an ocean world, but a vast volcanic landscape covered in lava plains, giant mountain ranges, fractured terrain, and impact craters. Later spacecraft missions dramatically improved these maps, revealing an entire world buried beneath the atmosphere like a hidden continent no human eye could directly see. One of the most important missions for understanding the surface was Magellan. Launched by NASA, the spacecraft used advanced radar imaging to map most of Venus in extraordinary detail during the early 1990s. Because cameras could not see through the clouds, Magellan relied on radar to create images of mountains, lava fields, valleys, volcanic structures, and cratered plains. The data completely transformed scientific understanding of Venus. Instead of a smooth, hidden world, scientists discovered a planet reshaped by massive geological forces over immense spans of time. Much of the surface consists of volcanic plains stretching for thousands of kilometers. These plains formed when lava erupted across huge regions of Venus and cooled into solid rock. Some areas appear relatively smooth in radar images, while others show complex patterns created by ancient lava flows. The scale of volcanism on Venus is enormous. Giant volcanoes rise from the plains, while lava channels snake across the terrain like dried rivers of stone. Some volcanic structures are larger than anything found on Earth. The entire planet appears heavily shaped by volcanic activity, suggesting that Venus may have experienced catastrophic resurfacing events in the distant past, where enormous amounts of lava flooded huge portions of the surface. The lack of water changes how the landscape evolves. On Earth, rain, rivers, glaciers, and oceans constantly reshape the surface through erosion. Mountains wear down over time, while valleys deepen under flowing water. Venus lacks these processes completely. There are no rivers cutting through rock, no rainfall reaching the ground, and no oceans smoothing the terrain. As a result, volcanic features and impact craters can remain preserved for immense periods of time. The surface appears dry, harsh, and strangely frozen despite the intense geological violence that may still continue below. One of the most famous regions on Venus is Maxwell Montes, the highest mountain range on the planet. Rising around 11 kilometers above the surrounding terrain, Maxwell Montes towers through the thick atmosphere like a giant wall of rock hidden beneath the clouds. The mountains are part of a larger highland region called Ishtar Terra, one of the main continental-sized elevated areas on Venus. Scientists often compare Ishtar Terra loosely to a continent because of its size and elevated terrain, although it formed through very different geological processes than Earth's continents. Radar images of Maxwell Montes revealed rough mountainous terrain, unlike the smoother volcanic plains elsewhere on the planet. Scientists believe tectonic forces may have pushed parts of the crust upward to create these enormous mountains. The pressure and heat on Venus make geology behave differently from Earth, but the existence of such massive elevated regions shows that powerful internal forces shape the planet's crust over time. Standing on Maxwell Montes would still be impossible for humans, because even at higher elevations, the atmosphere remains crushingly dense and dangerously hot. Another enormous region on Venus is Aphrodite Terra, a gigantic elevated area stretching across much of the equatorial region. Aphrodite Terra is larger than many continents on Earth and contains rugged terrain, fractured crust, and volcanic features spread across thousands of kilometers. Radar images revealed long fault systems, deformed surface structures, and signs of massive geological stress. The terrain looks torn apart in places, as though the crust itself cracked under internal pressure from below. Scientists believe hot material rising from deep inside Venus may have pushed upward against the surface, deforming the crust over long periods of time. The surface of Venus contains impact craters as well, though fewer than scientists expected at first. This became an important clue about the planet's geological history. On worlds like Mercury or the Moon, countless craters remain preserved because little erosion occurs and geological activity is minimal. Venus contains fewer craters because much of the surface may have been resurfaced by volcanic activity hundreds of millions of years ago. Lava flows could have buried older craters beneath fresh rock, effectively resetting large parts of the planetary surface. The craters that do exist often appear relatively well preserved because there is little water erosion to wear them down afterward. The atmosphere itself affects how impact craters form on Venus. Smaller meteors often burn up or break apart before reaching the ground because the atmosphere is so dense. This means Venus has fewer small craters compared to airless worlds like the Moon. Larger asteroids can still strike the surface, creating massive impact structures surrounded by ejector blankets and fractured terrain. Radar mapping revealed many of these craters scattered across the volcanic plains, their shapes preserved beneath the heavy atmosphere. One of the strangest aspects of Venusian geology is the growing evidence that the planet may still be volcanically active today. For decades, scientists debated whether Venus was geologically dead or still internally active. Recent discoveries increasingly suggest that volcanoes on Venus may still erupt in modern times. Infrared observations from orbit detected hotspots on the surface where temperatures appeared unusually high compared to surrounding areas. Some regions also showed changing atmospheric chemistry involving sulfur dioxide levels that may indicate recent volcanic eruptions releasing fresh gases into the atmosphere. The European spacecraft Venus Express provided some of the strongest evidence supporting possible modern volcanism. Infrared instruments detected thermal anomalies in certain volcanic regions, suggesting hot lava or recently resurfaced terrain might still exist. Scientists also observed changes in atmospheric sulfur dioxide concentrations over time. Since volcanic eruptions release sulfur gases into the atmosphere, these fluctuations raise the possibility that active volcanoes continue shaping Venus today. Even more dramatic evidence appeared when researchers compared radar images taken years apart. Some volcanic vents seem to have changed shape, suggesting fresh lava flows may have occurred between observations. One region showed signs of collapsing volcanic structures and newly formed lava deposits. If confirmed completely, this would mean Venus is not a frozen dead planet, but an active volcanic world still reshaping itself beneath the clouds. Massive eruptions may still occur hidden from direct view under the thick atmosphere. Volcanic activity on Venus likely behaves differently from volcanism on Earth because of the planet's extreme conditions. The surface temperatures are already hot enough to affect how lava cools and solidifies. The thick atmosphere changes how heat escapes from eruptions. Lava may flow differently under crushing atmospheric pressure compared to Earth. Scientists continue modeling these processes to understand how Venusian volcanoes operate inside such a hostile environment. The skies above the surface create one of the most disturbing environments imaginable. Because sunlight struggles to penetrate the thick atmosphere, the landscape exists under dim orange and brown lighting. The atmosphere scatters sunlight continuously through dense haze and cloud layers. Shadows would appear weak and blurry, while distant terrain fades into darkness quickly. A person standing there would not see a bright, open sky like Earth. Instead, the heavens would look heavy, smoky, and oppressive, hanging low above the landscape like a ceiling trapping the planet underneath. The Soviet Venera landers provided humanity's first actual glimpses of the surface. When the probes survived long enough after landing to transmit images, scientists finally saw the hidden world directly for the first time. The pictures revealed flat rocky plains covered with broken stones and dusty terrain beneath dim orange light. The atmosphere made the images appear strange and distorted compared to landscapes on Earth. Every photograph carried the terrifying knowledge that the spacecraft taking the images was slowly dying under extreme heat and pressure while transmitting them. The surface itself looked lifeless and brutal. Rocks scattered across the terrain appeared weathered by chemical interactions with the atmosphere rather than water erosion. The ground looked dry and ancient. There were no signs of movement except drifting haze in the atmosphere above. The thick air reduced visibility, while heat radiated from the ground continuously. Scientists examining the images realized they were looking at one of the most hostile landscapes ever photographed. The atmosphere near the surface is so dense that it creates a suffocating sense of confinement. Visibility remains limited because the thick air scatters light heavily. Even though the surface winds are relatively slow, the dense atmosphere carries enough force to move dust and particles across the landscape over time. A person standing there would feel surrounded by hot, heavy gas pressing from every direction. Breathing would be impossible. The heat would penetrate protective equipment rapidly, while the atmosphere transferred thermal energy into every exposed surface. The lack of water changes the chemistry of the rocks themselves. On Earth, water participates in countless geological processes, helping form minerals and reshape landscapes. Venus lacks liquid water entirely on the surface, creating different chemical interactions between the atmosphere and rocks. Scientists believe some surface materials react directly with the carbon dioxide atmosphere and sulfur compounds under high temperatures. Certain minerals may become unstable or chemically altered over time in ways rarely seen on Earth. Some regions of Venus contain strange geological structures unlike anything common on Earth. Scientists identified circular crack formations called coronae, believed to form when hot material rises beneath the crust and deforms the surface above. These features can span hundreds of kilometers and appear surrounded by fractures and lava flows. Other areas contain complex ridges, folded terrain, and tectonic deformation, suggesting immense internal stresses beneath the crust. Radar mapping became essential because ordinary cameras remained nearly useless from orbit. Visible light cannot penetrate the clouds effectively, meaning spacecraft relying only on standard imaging systems would see nothing but the upper atmosphere. Radar solved this problem by sending radio waves through the clouds and measuring how they reflected off the surface below. Different terrain types reflected radar differently, depending on roughness and composition, allowing scientists to create detailed maps despite never seeing the surface directly with human eyes. The combination of radar mapping, infrared studies, and lander missions slowly revealed the true nature of Venus. Beneath the clouds lies a volcanic world shaped by heat, pressure, tectonic forces, and chemical extremes. The planet feels less like a living world and more like the aftermath of planetary collapse. Every part of the environment works against survival. The atmosphere suffocates, the heat melts metal, acid clouds poison the sky, and below it all stretches an endless desert of volcanic rock under dim orange light. Modern missions continue investigating whether the surface remains geologically active today. Scientists want to know how often volcanoes erupt, how heat escapes from the interior, and whether Venus still experiences major resurfacing events. New radar systems and infrared instruments may soon provide even clearer evidence of active lava flows or changing terrain. Future landers may survive longer using advanced electronics designed for extreme environments, allowing scientists to study the surface directly for extended periods. Yet no matter how advanced technology becomes, Venus remains one of the most terrifying worlds humans have ever encountered. The landscape itself feels hostile on a planetary scale. Mountains rise through thick haze under dark skies. Lava plains stretch endlessly into the distance. Impact craters remain frozen in rock beneath crushing pressure. The atmosphere traps heat like a sealed furnace, while possible volcanoes continue shaping the surface from below. Everything about the world feels heavy, suffocating, and dead. And hidden somewhere beneath those endless volcanic plains, beneath the mountains and lava fields and shattered terrain, the planet may still be alive internally, still erupting, still reshaping itself inside the darkness beneath the clouds. The Soviet missions into hell. Long before modern space probes reached the planet, scientists already suspected Venus would be difficult to explore, but nobody fully understood just how violent and destructive the surface would turn out to be. When the first Soviet missions were designed, engineers expected extreme heat and pressure, but they still believed survival might last for a reasonable period of time on the surface. What followed was a sequence of missions that revealed a reality far more brutal than anything imagined, where spacecraft were not simply damaged or malfunctioning, but slowly destroyed by a planet that behaves like a machine built to crush and burn anything that enters it. The Soviet Venera program became the first and only successful attempt to land on Venus and send data back from the surface, and every success came at the cost of machines that were already dying the moment they touched the ground. The earliest attempts to reach Venus were failures that taught scientists how unforgiving the planet truly was. In the 1960s, spacecraft launched toward Venus often lost contact or broke apart during entry into the atmosphere. Some probes failed before even reaching the planet, while others entered the atmosphere but were crushed by pressure or destroyed by heat before they could transmit useful data. These early missions revealed that Venus was not a gentle or partially unknown world, but a place where physical conditions quickly overwhelmed engineering limits. Each failure forced engineers to rethink their designs completely. Ordinary spacecraft structures used for Earth orbit or lunar missions were not strong enough for Venus. The environment demanded something far more extreme, something capable of surviving pressures strong enough to crush steel and temperatures high enough to destroy electronics within minutes. As the Soviet space program continued its attempts, engineers began developing reinforced pressure vessels designed specifically for Venus. These were not delicate scientific instruments lightly protected for space travel. They were heavy, sealed metal spheres and cylinders built like deep-sea submarines, designed to protect sensitive electronics inside from the crushing atmosphere outside. The idea was simple, but terrifying in execution. Everything essential for survival had to be placed inside a structure strong enough to resist forces equivalent to being deep underwater on Earth, while also surviving temperatures hotter than industrial furnaces. Inside these protective shells were cameras, sensors, transmitters, and control systems that needed to function perfectly for as long as possible before the environment inevitably destroyed them. The Venera program eventually achieved one of the most significant milestones in planetary exploration history with Venera 7. This mission became the first spacecraft to successfully land on another planet and transmit data from the surface. Before Venera 7, many scientists doubted whether any probe could survive long enough to complete a landing on Venus. Engineers built the spacecraft with extreme care, reinforcing its structure and improving its thermal protection system. When it finally entered the atmosphere, the descent was slow and controlled compared to earlier failed missions. The spacecraft passed through thick clouds of sulfuric acid, experienced rising pressure and temperature, and continued descending toward the surface while transmitting data back to Earth. When Venera 7 finally reached the surface, it did not survive long, but it survived long enough to send back a historic signal. The probe recorded extreme conditions, including a temperature around 460 to 470 degrees Celsius and a pressure around 90 times that of Earth's atmosphere. These numbers confirmed that Venus was far more hostile than previously believed. The surface was not just hot or dense, it was an environment where ordinary physical systems began to fail rapidly. The lander transmitted weak signals for a short period before going silent forever. But that brief transmission proved that landing on Venus was possible and that data could be retrieved directly from the surface. Later missions improved on this achievement. Venera 9 marked a major breakthrough when it successfully transmitted the first images from the surface of Venus. These images were not clear, high-resolution photographs like those taken on Earth or Mars. Instead, they were grainy, distorted, and limited by the extreme conditions in which they were captured. But they showed something humanity had never seen before: the actual surface of Venus. The images revealed rocky terrain scattered with stones under a dim orange sky. The land looked dry, broken, and lifeless, with no visible signs of water or erosion. The spacecraft itself was slowly being destroyed while capturing these images, as heat and pressure gradually overwhelmed its systems. Even more advanced was Venera 13, which provided the most detailed colour images and scientific data ever obtained from the Venusian surface. This mission carried improved cameras and more advanced sensors capable of surviving slightly longer under extreme conditions. When Venera 13 landed, it transmitted colour photographs showing a harsh, rocky landscape beneath a yellow-orange sky. The colours revealed a world dominated by reddish-brown rocks and dusty terrain under thick atmospheric haze. Alongside images, the spacecraft also recorded sound data from the Venusian environment, capturing faint mechanical and atmospheric noises transmitted through the dense air. These recordings, although limited, provided an eerie sense of presence on another world, as if the planet itself was slowly consuming the machine while it attempted to speak back to Earth. Each Venera mission followed a similar pattern of descent, landing, brief survival, and eventual destruction. The spacecraft would enter the atmosphere and begin a controlled fall through thick clouds filled with sulfuric acid. During descent, instruments recorded temperature increases, pressure changes, and atmospheric composition. The surrounding clouds gradually shifted from bright reflective layers high above the planet to darker, denser regions closer to the surface. As the probe descended further, the heat became more intense and the pressure increased steadily. Inside the spacecraft, cooling systems worked continuously, but they could only delay the inevitable. Electronics began heating up, protective materials started degrading, and internal systems operated under increasing stress. When the landers finally reached the surface, the environment immediately began destroying them. The ground temperature alone was hot enough to damage electronics and weaken structural components. The pressure crushed against every surface of the spacecraft, testing every seal and weld. Metal parts expanded under heat while simultaneously being compressed by the atmosphere. Electrical systems became unstable as insulation broke down under extreme conditions. Communication signals weakened as the environment interfered with transmission. The spacecraft did not explode or fail suddenly. Instead, it died slowly as each system gradually stopped functioning one by one until silence took over completely. One of the most powerful aspects of the Venera missions is the emotional weight carried by their transmissions. These were not just data points or scientific readings. They were final messages from machines standing on another world, slowly being destroyed while still attempting to communicate. Each signal received on Earth represented a brief window into an environment so extreme that survival was measured in minutes. Scientists listening to these transmissions were not hearing stable operations. They were hearing systems under stress, struggling to function while the planet itself overwhelmed them. The temperature readings alone were shocking. Venus consistently recorded surface temperatures around 470 degrees Celsius. This level of heat is enough to melt lead and damage most electronic systems designed for space exploration. The pressure readings were equally extreme, showing values around 90 bar, similar to conditions found deep underwater on Earth, but spread across an entire planet. These measurements confirmed that Venus was not just hot or dense in isolated regions, but uniformly extreme across its entire surface. The composition of the surface also became clearer through these missions. The land appeared to consist mostly of volcanic rock, shaped by ancient lava flows and possibly ongoing volcanic activity. There was no evidence of liquid water, no signs of sedimentary erosion, and no biological activity. Instead, the surface was a dry, rocky desert under a thick atmosphere that blocks most sunlight. The landscape appeared stable but lifeless, shaped by heat and volcanic processes rather than weather systems involving water. The emotional impact of these missions on scientists cannot be separated from the technical achievements. Each time a probe landed successfully, it meant that humanity had reached another world, but only briefly before losing contact forever. The spacecraft were never recovered. They remained on Venus, silent and destroyed, sitting on a planet where conditions ensured nothing could survive for long. Engineers knew this outcome in advance, yet each successful transmission still carried a sense of finality. These were machines speaking their last words from a place no human could ever survive. The descent sequences of these missions were carefully studied and reconstructed later using data and simulation. As spacecraft entered the atmosphere, they passed through thick cloud layers filled with sulfuric acid droplets. These clouds gradually gave way to denser atmospheric regions where heat and pressure increased dramatically. The descent was not smooth. Turbulence shook the spacecraft while atmospheric conditions shifted continuously. Instruments recorded changing temperatures and pressure levels as the probe moved closer to the surface. Engineers later recreated these sequences visually to understand exactly how each system responded under stress. Inside mission recordings, static filled communication channels as signals weakened during descent and landing. These recordings are some of the most haunting artifacts of planetary exploration because they represent machines operating under conditions far beyond their design limits. The static is not just noise, it is the sound of systems struggling to function while the environment gradually destroys them. Every drop in signal strength represents another step closer to failure. The final moments of each mission are always similar. After landing, the spacecraft continues transmitting for a short time while temperatures rise and pressure builds. Then systems begin failing one by one. Sensors stop responding. Communication weakens. Internal components overheat. Eventually, the signal cuts out completely, leaving only silence. That silence represents the end of human contact with a machine on another world, not because the mission is complete, but because the environment has won. One of the most remarkable achievements came when Venera missions captured panoramic images of the surface. These images, though limited in quality, showed wide views of Venusian terrain stretching into the distance. The landscapes appeared flat and rocky, with scattered stones and broken surfaces under a dim orange sky. The horizon looked hazy due to the thick atmosphere. There were no signs of movement or life, only stillness under extreme conditions. These panoramic views remain some of the most important visual records ever obtained from another planet. The Venera program ultimately demonstrated both the power and limits of human engineering. It proved that spacecraft could reach the surface of Venus and transmit valuable scientific data. But it also revealed how quickly that environment destroys machines. Every mission was a race against time, a short window of survival inside a world designed by nature to crush, burn, and dissolve anything that enters it. Modern missions continue building on this legacy. NASA and other space agencies are designing new probes capable of surviving longer on Venus, using improved materials, stronger cooling systems, and more advanced electronics. Scientists hope to extend mission lifetimes from minutes to hours, or even longer, allowing more detailed exploration of the surface and atmosphere. Yet even with these advances, Venus remains one of the most extreme environments ever targeted for exploration. What happened to Venus? Venus may have started as a world that was not too different from Earth. Many scientists think it once had oceans, milder temperatures, and a thicker atmosphere that could have supported a stable climate for a long time. But over time, the planet changed completely, and the system that once kept it stable broke down. The leading idea is that Venus suffered a runaway greenhouse effect. This means the planet slowly trapped more and more heat in its atmosphere until the temperature rose beyond control. As the sun's energy heated the surface, any water that existed began to evaporate into the air. Water vapor is itself a strong greenhouse gas, so it trapped even more heat, which caused even more water to evaporate. This cycle kept feeding itself until the oceans likely boiled away into space. Once water reached the upper atmosphere, sunlight broke it apart into hydrogen and oxygen. The hydrogen was light enough to escape into space over time, slowly removing Venus's water supply. This process is supported by measurements of deuterium, a heavier form of hydrogen. Venus has a much higher ratio of deuterium compared to Earth, which strongly suggests that large amounts of normal hydrogen have already been lost. This is one of the strongest clues that Venus once had far more water than it does today. At the same time, the carbon cycle on Venus failed in a major way. On Earth, carbon dioxide is constantly recycled between the atmosphere, oceans, and rocks. Plate tectonics helps lock carbon into the planet's interior and later release it again through volcanic activity. Venus does not appear to have active plate tectonics like Earth. Instead, its surface behaves like a single, rigid shell. This means carbon dioxide released by volcanoes stays in the atmosphere instead of being absorbed by oceans or recycled underground. Over time, this caused carbon dioxide to build up to extreme levels, thickening the atmosphere and trapping even more heat. As the atmosphere became denser, the greenhouse effect intensified further. Heat that entered the planet had no easy way to escape back into space. This created a stable but extreme condition where Venus locked itself into a permanent high-temperature state. Today, surface temperatures remain around 465 degrees Celsius, hot enough to melt lead. The temperature is nearly the same across the entire planet because the thick atmosphere distributes heat efficiently, leaving no real difference between day and night. Scientists also study Venus's atmosphere using isotopes, especially deuterium, to understand how much water was lost. The high deuterium levels strongly support the idea that Venus once had a large amount of water. Over time, hydrogen escaped into space, while oxygen was absorbed into rocks or lost through chemical reactions. Without water, the planet lost one of the key systems that stabilizes climate on Earth. When comparing Earth and Venus, the difference comes down to small changes that had huge long-term effects. Earth kept its oceans, active plate tectonics, and stable carbon cycle. Venus likely lost its water early, which triggered climate instability. Once that instability began, the planet slowly moved into a state where heat, pressure, and atmospheric chemistry reinforced each other. Two similar planets ended up in completely different conditions because of small differences that changed everything over millions of years. Today, scientists still look for signs of possible activity on Venus. Some evidence suggests volcanic activity may still occur. Infrared measurements have detected regions that appear hotter than surrounding areas, which could be linked to recent lava flows. Changes in atmospheric sulfur dioxide levels also suggest possible volcanic releases. This means Venus might not be a completely dead world, but one that is still slowly changing beneath its thick clouds. One of the most debated topics in modern Venus research is whether there could be life in the upper clouds. In 2020, scientists reported a possible detection of phosphine gas in the atmosphere. On Earth, phosphine is associated with biological processes or industrial activity. This created excitement because the upper cloud layers of Venus, about 50 to 60 kilometers above the surface, have temperatures and pressures that are much closer to Earth-like conditions. In this region, it is cold enough for liquid droplets to exist, although they are made of sulfuric acid instead of water. However, the phosphine detection is highly disputed. Other studies suggested the signal could be due to errors in data processing or unknown chemical reactions rather than life. So far, there is no confirmed evidence of biology on Venus. Still, the idea remains scientifically interesting because it forces researchers to examine whether unknown chemistry could exist in the clouds. Some scientists also point out that certain extremophile microbes on Earth can survive in highly acidic environments, showing that life can adapt to harsh conditions, even though Venus is far more extreme. Because of these questions, space agencies are once again focusing on Venus. NASA is preparing missions like Da Vinci and Veritas, while the European Space Agency is developing Envision. These missions aim to study the atmosphere, map the surface in detail, and look for signs of recent volcanic activity. Scientists want to understand how Venus changed from a potentially Earth-like planet into its current extreme state. These missions will use improved radar systems, atmospheric probes, and heat-resistant electronics designed to survive longer in Venus's environment. One of the main goals is to understand the planet's climate history and figure out exactly when and how the runaway greenhouse effect took over. Another goal is to learn whether Venus is still geologically active today, which could help explain how its atmosphere continues to evolve. To understand what Venus is like, scientists often describe a full descent through its atmosphere. A spacecraft entering Venus first hits thick clouds made of sulfuric acid. The descent is violent, with strong turbulence shaking the probe as it falls. As it moves deeper, the atmosphere becomes thicker and hotter. Acid droplets begin to coat the spacecraft, while pressure increases steadily. Communication becomes harder as signals weaken through dense clouds. Eventually, the spacecraft reaches the lower atmosphere, where heat and pressure rise to extreme levels. Electronics begin to fail, and cooling systems struggle to keep up. When the probe reaches the surface, it lands in a world of crushing pressure, intense heat, and dim orange light. Systems start failing almost immediately. Communication drops slowly until the final signal is lost. Within a short time, the spacecraft becomes silent, unable to survive the environment around it. Venus today stands as one of the most extreme examples of planetary change in the solar system.